Hello there. Welcome. I am so glad you have found your way here tonight. Before we begin our journey into the furthest reaches of the cosmos, I invite you to take a moment to truly settle in. This is your time. Adjust your pillows until they feel just right. Pull the blankets up to your chin, or perhaps let your arms rest loosely by your sides. Find that perfect position where your shoulders can finally drop and where the tension in your jaw can simply melt away. You might want to adjust your volume now. Set it to a level where my voice feels like a soft, warm hum, a gentle presence in the room that doesn't demand too much of your attention. Just let the words wash over you like a slow-moving tide. Tonight, we are going to explore ideas that are sometimes whispered in the halls of physics as forbidden or bold. In the world of science, these words don't mean something scary or dangerous. Instead, they represent the theories that sit right at the edge of our current maps. They are the thoughts that challenge the very foundation of what we think is real, pushing against the boundaries of the comfortable and the known. They are forbidden only in the sense that they ask us to imagine the impossible, to look past the sturdy walls of our everyday lives and into the vast, silent mystery of the deep universe. Think for a moment about our most powerful telescopes, those magnificent structures of glass and gold, drifting in the cold, quiet dark. Even they have a limit. There is a cosmic horizon, a point beyond which light has not yet had time to reach us. It is a curtain of shadow that hides the true scale of reality. But where our eyes fail, our minds begin to soar. It is in that quiet, hidden space that the most daring ideas live, waiting to be understood. As we move through these concepts tonight, I want you to feel a sense of profound peace. We aren't here to solve every mystery, but to marvel at them. Let the sheer scale of the stars and the infinite nature of time make your own worries feel small, light, and distant, like tiny grains of sand drifting away into a calm, dark ocean. We are going on a journey through the unknown, designed specifically to soothe your mind and prepare you for a deep, restful sleep. We will begin our exploration at the very start of it all, the origin of everything. We often hear about the birth of the universe as a single, explosive moment. But what if that was just one chapter in a much longer story? What if the beginning wasn't actually the beginning? What if the darkness that came before held its own secrets? Before we drift further into the stars, if you enjoy these nightly journeys of discovery and find comfort in our shared curiosity, I invite you to gently subscribe and join our sleepy community. It is a quiet space for all of us to learn, to wonder, and to find rest together, night after night. Now, take one more slow, deep breath. Feel the air fill your lungs and let it out slowly. We are ready to begin. Our story starts long ago, at the very threshold of time itself. The Big Bang is the story we have all been told, the standard model that explains how our universe began as a tiny, infinitely hot point and expanded into the vastness we see today. It is a powerful and elegant idea, backed by decades of observation and the faint, glowing after-image of the early cosmos. But for some scientists, a question lingers in the quiet hours of the night. What came before that first moment? If the universe is expanding today, it must have been smaller yesterday. But does that mean it started from absolutely nothing? Some physicists whisper about a different possibility, a theory known as the Big Bounce. In this view, our universe didn't just burst into existence from a void. Instead, it is just one chapter in an ancient, repeating story. Imagine, if you will, a great cosmic lung. It expands outward, filling with light and matter, and then, after billions upon billions of years, it begins to slowly, gently contract. Gravity, the silent architect of the stars, eventually pulls everything back together, drawing the galaxies home. This big crunch isn't an ending, but a transition. As everything draws inward, the universe becomes incredibly dense and hot. But before it can collapse into nothingness, it bounces. Like a ball hitting the floor or a soft spring being compressed, it reaches a physical limit and then pushes back, beginning a brand new expansion, a new Big Bang. This idea introduces a fascinating tension into our understanding of reality. We usually think of time as a straight line, a path with a clear beginning and a distant, fading end. But the Big Bounce suggests that time might be a circle, or perhaps a spiral. It asks us to consider if the beginning is simply a human concept, a label we put on a process that has no true start and no final conclusion. It challenges the idea of a day without a yesterday. There is a deep rhythmic comfort in this vision of the cosmos. It suggests a universe that is alive in its own way, breathing in and out over trillions of years. It means that the atoms that make up your body, the light from the sun, and the dust of the distant nebula have all been here before, in different forms, in previous cycles of existence. You are part of a grand eternal pulse that has been beating since forever. Just as your own breath moves in and out without you having to think about it, the universe may simply exist in this state of perpetual motion. It is a stable, reliable process. In this model, nothing is ever truly lost. It is simply recycled into the next great blooming of stars. It is a universe of second chances. As we sit with this idea of a breathing universe, we can begin to look at even more specific ways this cycle might work. Some thinkers have taken this concept and refined it, looking for the physical evidence of these previous worlds. They wonder if the universe doesn't just bounce, but undergoes a more elegant transformation, a shift in the very fabric of space and time that allows one era to fade into the next, leaving behind faint clues of what used to be. One of the most elegant versions of this repeating story comes from the mind of Sir Roger Penrose, a Nobel laureate who looks at the stars and sees a sequence of cosmic ages he calls aeons. His theory is known as conformal cosmology, or CCC for short. It is a big name for a very gentle and beautiful idea. Imagine a universe that expands so far and for so long that it eventually forgets how big it is. You see, in the very distant future, after trillions upon trillions of years, all the matter we see today, the stars, the planets, even the stray atoms, will have decayed. All that will be left is light, and particles that behave like light. And light, as far as the laws of physics are concerned, does not experience time or distance. in the way we do. To a photon, a billion miles is no different from a single inch. Without anything solid to measure against, the universe loses its sense of scale. The infinite, cold and empty void of the far future becomes mathematically identical to the tiny, hot, and dense point of a new Big Bang. The end of one eon simply becomes the beginning of the next. Like a seam in a piece of silk so fine you cannot even feel it. But Penrose suggests something even more profound. He believes that these previous worlds might have left fingerprints behind for us to find. He calls them Hawking points. You might think of them as faint, circular bruises on the skin of the sky. These points are the ghostly remains of supermassive black holes from the universe that existed before ours. When those ancient black holes have finally evaporated after an eternity of silence, they released a final enormous burst of energy that was so powerful it survived the transition into our current reality. Scientists look for these marks within the oldest light we can see, the cosmic microwave background, which is the afterglow of our own beginning. Finding these circles would be like finding a pressed flower inside an old book, a delicate reminder of a life lived long ago. It is a stirring thought to hold as you drift toward sleep. We may not be living in a lonely, isolated bubble of time. Instead, we may be walking through the echoes of a past world. The very structure of our sky might be a map of a history that stretches back long before our own sun was even a cloud of dust. We are the inheritors of a cosmic legacy, carrying the faint memories of a previous universe in the cold reaches of space. It makes the cosmos feel less like a cold vacuum and more like an ancient library where every page has been turned before and every story is part of a much larger, infinite volume. This vision of a single, repeating universe is vast, but it is only one possibility. Some scientists look at these echoes and wonder if they aren't just remnants of our own past, but signs of something even more expansive. They begin to ask, what if our universe is not alone in its cycle? What if, instead of one lung breathing in and out, there is a vast ocean of bubbles, each one a universe of its own, drifting in a sea of infinite possibility? Imagine for a moment that our entire universe, everything we have ever seen, every star and every galaxy, is just a single, fragile bubble in a vast, foaming ocean. This is the essence of the multiverse theory, a concept that stretches our imagination to its very limits. If the idea of a repeating universe felt large, the multiverse is larger still. It suggests that what we call the universe is actually just one small part of a much greater structure, a tiny pocket of calm in an infinite sea of creation. To understand how this might happen, we look at a process called eternal inflation. Scientists believe that in the very first moments after the Big Bang, space expanded at an incredible, dizzying speed. But while that expansion slowed down in our neck of the woods, allowing stars and planets to form, some theories suggest that in other places, the expansion never stopped. It continues forever, a restless, high-energy background that is constantly stretching and growing. Every so often, a small patch of this inflating space slows down and settles like a bubble forming in a pot of boiling water. That bubble becomes a universe of its own, with its own laws of physics, its own stars, and perhaps its own life. It is a beautiful, if somewhat bold, image, a cosmic sea where new universes are constantly branching off, drifting away from one another into the infinite dark. However, this theory brings with it a certain scientific tension. Because these bubbles are moving away from us faster than the speed of light, we can never visit them. We can never send a probe to see what they look like, and we can never receive a signal from a neighbor. We are forever separated by the growing space between us. Because of this, some scientists feel a bit uneasy. They wonder if a theory that can never be observed or tested still counts as science, or if it has crossed over into the realm of philosophy. They call it unscientific because it sits forever beyond the reach of our telescopes, a secret the universe may never choose to share. Yet, even with that uncertainty, there is a profound sense of comfort to be found in this idea of infinite possibility. In a landscape this vast, nothing is truly impossible. If there are an infinite number of these bubbles, then every variation of reality exists somewhere. It means the cosmic landscape is not a cold, empty void, but a lush and varied garden of existence, blooming in ways we can only dream of. It takes the weight off our shoulders, knowing that we are part of a grand, eternal process that is much bigger than our own worries or our own fleeting moments. The universe becomes a place of endless discovery, even if those discoveries remain tucked away in other bubbles of time. But as we contemplate these physical bubbles drifting in space, we find that the mystery goes even deeper. Some physicists suggest we don't need to look to the distant reaches of the inflating cosmos to find other worlds. They believe that these alternate realities are much closer than we think, perhaps as close as the very air around us. They suggest that every choice, every movement of an atom, and every flicker of light might be creating a new branch of reality right here, in a version of the multiverse that exists not in the distances of space, but in the strange, shimmering logic of the quantum world. Imagine, for a moment, a choice you made today, a very simple one. Perhaps you chose to have a glass of water, or perhaps you decided to look out the window at a passing cloud. In our everyday experience, we see only the path we took. The other options seem to vanish, becoming nothing more than what-ifs or fading memories of a decision made. But in the silent, microscopic world of quantum physics, there is a theory that suggests nothing ever truly vanishes. This is the many worlds interpretation, a concept that is as bold as it is beautiful. To understand this, we have to look at the way subatomic particles behave. In the quantum realm, particles don't exist in just one certain spot. Instead, they exist in a state of superposition, which is a gentle way of saying they are in many places or many states all at once. It is only when we look at them, when we measure them, that they seem to settle into a single position. For decades, scientists wondered where all those other possibilities went when we looked away. In the late 1950s, a physicist named Hugh Everett proposed a stunning answer. They don't go anywhere. Instead, the universe itself splits. According to this theory, every time a quantum event occurs, which is happening trillions of times every second within every atom of your body, the universe branches. It is like a tree that is constantly growing new limbs, each one representing a different version of reality. In one branch, that particle moved left. In another, it moved right. And because we are made of these particles, we branch along with them. At first, this might feel a little overwhelming. There is a certain tension in the thought of infinite versions of yourself, living out infinite lives in a vast, branching thicket of realities. It can feel as though our individual lives are less unique. But if we look at it through a softer lens, there is a deep and quiet comfort to be found here in the many worlds. Interpretation, no path is ever truly lost. Every dream you didn't pursue, every wrong turn you think you took, and every missed opportunity is being realized somewhere in the grand tapestry of the multiverse. It suggests that the universe is far more generous than we ever imagined. It isn't a place of either or, but a place of and. Every possibility is explored, every story is told. It reframes our reality not as a single fragile thread, but as a rich, shimmering fabric where every path is taken and every potential is fulfilled. We are simply experiencing one beautiful, coherent narrative in a library of infinite volumes. This realization brings a sense of lightness. It reminds us that the universe is much larger and more complex than our five senses can perceive. We are only seeing a tiny, thin slice of a much thicker, more vibrant reality. We are like listeners hearing a single melody, unaware that it is part of a massive, eternal symphony playing in the rooms all around us. It encourages us to let go of regret and embrace the mystery of our own existence, knowing that we are part of a boundless, unfolding creation. But as we sit with the idea of these infinite branching worlds, we might begin to wonder about the nature of the here and now. If reality can split so easily, what is it actually made of? Is it as solid as it feels, or is the world we touch and see just the surface of something else? Some scientists suggest that even these infinite worlds are just the beginning, and that the very space we inhabit might be a kind of illusion, a clever projection of information that is far simpler and far stranger than it appears. It leads us to wonder if the three-dimensional world we call home is actually a beautiful, shimmering projection, much like a hologram caught in the light. Take a slow, deep breath. Feel the weight of your body against the bed. It feels sealed, doesn't it? The mattress beneath you, the cool air against your skin, the very walls of the room around you. But some of the most profound thinkers in modern physics suggest that this solidity is a kind of beautiful trick. This brings us to a concept known as the holographic principle. The idea that our entire three-dimensional universe might actually be a projection of information stored on a distant two-dimensional surface. To understand this, think of the small, shimmering hologram on a credit card. When you tilt it in the light, a bird or a logo seems to pop out in 3 dimensions. You can see depth, you can see movement, and it looks like a solid object with volume. Yet you know that the information creating that image is actually printed on a flat, 2-dimensional piece of plastic. Or consider a cinema screen. When you watch a film, you see a vast landscape, a deep rolling ocean, or a distant star system. Your mind perceives the depth and the distance, but in reality, it is all just light dancing on a flat white surface. Scientists are exploring the possibility that we are living inside a cosmic version of this. They suggest that everything we see, the distant galaxies, the trees outside your window, even the very atoms that make up your hands, is a three-dimensional hologram projected from data residing at the very edge of the observable universe. This isn't just a flight of fancy. It emerges from a very specific and rigorous place in mathematics, the study of black holes. For a long time, there was a great mystery about what happens to information when it falls into a black hole. Does it simply vanish? Physicists like Stephen Hawking and Leonard Susskind realized that the information might actually be preserved on the event horizon, the flat two-dimensional boundary of the black hole. Remarkably, the math showed that the surface area of a black hole could hold every bit of information about the three-dimensional objects that fell inside. If a black hole can store its three-dimensional history on a two-dimensional surface, some theorists argue, perhaps the entire universe does the same. It creates a gentle tension in our understanding of reality, a shift from seeing the world as a collection of solid things to seeing it as a vast, interconnected web of data. There is a wonderful sense of lightness in this idea. If the world is a projection, then the heavy, solid worries of our day-to-day lives are a bit like shadows moving across a screen. They are real in their own way, and they matter, but they aren't quite as dense or as permanent as they feel. It transforms the cosmos from a cold, heavy machine into something more like a grand, silent light show. We are made of light and information, drifting through a world that is far more delicate and ethereal than we ever dare to imagine. It is a soft, glowing reality where the boundaries between objects are just the shimmering edges of a much larger, simpler truth. As you settle deeper into your pillows, let that feeling of weightlessness stay with you. If our reality is built on bits of information, it brings us to a question that has moved from the realm of science fiction into serious scientific debate. If the universe is a projection of data, where does that data come from? Is it a natural, ancient property of the fabric of space? Or could it be something even more structured? If we are, in a sense, made of code, it leads us to wonder about the nature of the projector itself. It brings us to a theory that suggests our entire existence might be a sophisticated, purposeful creation, a grand digital dream that feels as real as the breath you are taking right now. If we follow that thread of information and projection to its furthest edge, we arrive at a question that has fascinated both philosophers and physicists alike. Are we living in a computer simulation? It's an idea that might sound like a story from a book, but it is rooted in a very logical progression of thought. Think for a moment about how far our own technology has come in just a few decades. We went from simple, flickering dots on a screen to vast, immersive digital worlds that we can almost touch. If we project that progress forward by thousands or even millions of years, it's not hard to imagine a civilization capable of creating a simulation so perfect, so detailed, that the beings inside it would have no way of knowing they were part of a program. This is the core of an argument popularized by the philosopher Nick Bostrom. He suggests that if such simulations are possible, an advanced society would likely run thousands of them to study history, science, or simply for the sake of creation. Statistically, that would mean there are many more simulated realities than there are real ones. In that vast sea of possibilities, the odds of us being in the original base reality would be very small. It's a thought that challenges our sense of what is solid and true, suggesting that the laws of physics we study might actually be the lines of code in a grand cosmic software. Of course, this theory creates a gentle tension within the scientific community. Many physicists are hesitant to embrace it fully, often dismissing it as more of a philosophical puzzle than a testable science. To a physicist, a theory needs evidence, a glitch in the system, or perhaps a limit to how small or how fast things can move that hints at a digital structure. Without that proof, it remains a whisper of a possibility, a what if, that lingers in the back of the mind. Some look for rounding errors in the math of the universe, while others believe that the very fact that our universe follows such precise mathematical rules is the greatest hint of all. But as you lie here, safe and warm, there is a deep comfort to be found regardless of the answer. Whether our universe is made of physical atoms or digital bits, your experiences remain entirely valid and deeply meaningful. The warmth of a cup of tea, the soft weight of your blanket, and the quiet rhythm of your breath are real because you feel them. A simulation of a sunset is still a sunset if it brings you peace. Our feelings, our connections, and our wonders are not diminished by the nature of the stage they are performed on. The meaning of our lives isn't found in what the universe is made of, but in how we experience the journey through it. Even as we ponder the nature of this reality, we realize that there are parts of our world that seem to defy our understanding entirely. As we look out into the great expanse of space, we find that the stars and galaxies we can see are only a tiny fraction of what is actually there. There is a hidden side to the cosmos, a mysterious, invisible substance that provides the scaffolding for everything we know. It is a mystery that suggests that even if we are in a simulation or a hologram or a physical machine, the vast majority of our universe is still waiting to be discovered, hidden in a shadow we are only just beginning to name. As we drift further into the cosmic ocean, we encounter one of the most persistent and quiet mysteries of modern science: dark matter. Imagine for a moment that you are looking at a beautiful swirling galaxy, a glowing spiral of billions of stars. For decades, scientists believed that what we see is what we get, that the stars, the gas, and the dust made up the entirety of that galaxy's mass. But as they looked closer, they noticed something strange. The stars at the very edges of these galaxies were moving much faster than they should be. Based on the laws of physics, there simply wasn't enough visible matter to create the gravity needed to hold on to those fast-moving stars. By all accounts, the galaxies should be flying apart, their stars skittering into the void like water droplets, spinning off a wet umbrella. But they don't fly apart. They stay held together in a perfect graceful dance. To explain this, scientists propose that there must be an invisible glue providing an extra gravitational hug, keeping everything in its place. We call this substance dark matter. It is dark, not because it is scary or black, but because it is truly silent and invisible. It does not emit light, it does not reflect it, and it does not block it. It is a ghost-like presence that passes right through us, through your room and through the earth itself, without leaving a trace. It is the invisible scaffolding of the universe, making up about 85% of all the matter in the cosmos. We cannot touch it, but we can see its heavy footprint in the way it bends light and steers the stars. However, there is a bold and fascinating theory that challenges this entire idea. What if we have been looking for a ghost that doesn't actually exist? What if the reason we can't find dark matter particles is that there are no particles to find? Some scientists suggest that the problem isn't missing matter, but rather our missing understanding of how gravity works over vast distances. This is a concept known as MOND, or modified Newtonian dynamics. Think of gravity like a musical instrument that sounds slightly different when played very softly. Mond suggests that Newton's laws of gravity, which work perfectly here on Earth and within our solar system, might change just a little bit when gravity becomes incredibly weak, such as in the lonely, quiet outskirts of a galaxy. In these regions, gravity might be naturally stronger than our current formulas predict. If this is true, the extra pull we see isn't coming from invisible matter, but from a more nuanced and elegant law of nature that we are only just beginning to grasp. There is something deeply peaceful about this possibility. It suggests a universe that is self-contained and orderly, where we don't need to invent invisible substances to explain the beauty we see. It reminds us that even our most fundamental truths are invitations to look closer and think more deeply. It is a reminder that the universe is always ready to surprise us with a simpler, more beautiful answer than we ever imagined. But even as we ponder the rules that hold the galaxies together, we realize that gravity is only half of the story. While gravity is a gentle pull inward, there is another, more mysterious presence in the dark that is doing the exact opposite. It is a force that doesn't just fill the space between the stars, but seems to be stretching the very fabric of the universe itself, pushing everything further and further apart into the infinite night. Close your eyes for a moment and imagine the space between the stars. It seems empty, a vast and silent vacuum. But science tells us that this emptiness is far from quiet. It is filled with a restless energy that we are only just beginning to understand. We call it dark energy, and it acts like a silent, invisible wind, pushing the galaxies apart and stretching the very fabric of the cosmos. If dark matter is the gravity that holds the stars in their orbits, dark energy is the force that ensures the universe continues to grow wider and deeper every single second. In the standard models of physics, this energy is often thought to be a constant, a steady, unchanging pressure inherent to space itself. But there is a bolder idea, one that feels more like a living pulse. Some physicists call it quintessence. The name is borrowed from the ancient philosophers who believed that beyond the four elements of earth, air, fire, and water, there existed a fifth element, a pure celestial essence that filled the heavens. In our modern understanding, quintessence is a theoretical fifth fundamental force of nature, joining the ranks of gravity, electromagnetism, and the strong and weak nuclear forces. What makes quintessence so intriguing is that, unlike a constant energy, it can change. It is a field that evolves over time, shifting its strength as the universe ages. It is like the changing light of a late afternoon softening as the sun sinks lower, or perhaps like the slow, rhythmic breathing of a person in deep sleep. This means that the push of the universe isn't a fixed mechanical rule, but a dynamic process. It suggests that the vacuum of space is not a dead, empty stage, but a medium that can respond, adapt, and flow. There is a certain tension in this theory, a mystery that challenges our predictions of the far future. If this fifth force were to grow significantly stronger over billions of years, it might eventually become powerful enough to overcome the gravity of galaxies, pulling them apart until every star and every planet is isolated in its own private darkness, a concept sometimes called the Big Rip. If it were to weaken, the expansion of the universe might slow down or even begin to reverse. But rather than being a source of worry, this uncertainty reminds us of how much there is still to learn. It paints a picture of a universe that is not a clockwork machine winding down in a predictable way, but an evolving masterpiece that is still being written. There is a profound peace in realizing that the cosmos is not a static void. It is active, filled with invisible currents and shifting fields that guide the destiny of every star. We are part of a grand unfolding dance where even the empty space around us is alive with potential. It is a reminder that the universe is never truly empty. It is always full of possibility, waiting for the next chapter of its own quiet history to begin. But while dark energy works on the largest scales, pushing the boundaries of the universe outward, there are places where gravity is so intense that it creates a total reversal of this expansion. There are points in space where matter has become so concentrated that it creates a pocket of absolute silence, where the pull is so great that not even light can find its way out. To understand the true limits of our reality, we must turn our gaze away from the infinite expansion and toward the dark, heavy hearts of the galaxies. We must look into the center of a black hole. Imagine, for a moment, standing at the edge of a great mystery. We have spent time looking at the vast outward push of the universe, but now we must turn our attention to the places where gravity has won the ultimate victory. We are looking toward the center of a black hole, a place that has captured the human imagination for decades. For a long time, the traditional view of a black hole was one of a great, dark silence. We were told that at its very heart lies something called a singularity, a point where an immense amount of matter has been crushed into a space so small that it essentially has no volume at all. In this tiny, invisible point, the density becomes infinite, and the laws of physics as we know them simply cease to function. Our math, which works so beautifully to describe the orbits of planets and the glow of stars begins to whisper, "I don't know," when it reaches the singularity. This idea of a singularity can feel a bit unsettling, like a tear in the fabric of reality or a cold, empty void where information is lost forever. It suggests a bottom to the universe that we can never truly understand. But science is always evolving, and some of the most daring minds in physics have proposed a different, perhaps more comforting vision of what lies inside. This is the fuzzball theory, a concept born from the intricate math of string theory. In this view, a black hole is not a hollow shell with a terrifying point of nothingness at its center. Instead, the entire black hole is a solid, though incredibly exotic object. Imagine a ball of yarn made of countless tiny vibrating strings. These strings are the fundamental building blocks of everything in existence. In a fuzzball, these strings are tangled and woven together so tightly that they create a physical surface. There is no empty space inside and no singularity at the core. Instead of a hole, we find a complex, textured, and vibrating sphere of energy. This shift in perspective changes everything. It replaces the idea of a scary, destructive void with a structure that is rich and full of information. Like a library where every book has been pressed together into a single massive volume, the fuzzball holds on to the history of everything that ever fell into it. It is not a place where things are deleted from existence, but a place where they are transformed into a new, stable state. It is a dense, quiet archive of the cosmos, humming with the subtle vibrations of a trillion strings. There is a profound peace in this idea. It suggests that the universe is never truly broken, and that even in the most extreme conditions, there is order and structure. The fuzz of the black hole is a soft, complex reality that shields us from the impossible infinities of a singularity. It makes the dark places of the universe feel a little less like a nothing and a little more like a something, a deep, heavy, and mysterious state of matter that we are only just beginning to comprehend. But as we contemplate these heavy, silent spheres, a new question naturally arises. If gravity can pull matter so tightly together that it forms these dense archives of light and energy, is there a limit to how much they can hold? If the universe has places where matter can only enter, never to return, could there be a mirror to this process? Could there be a doorway on the other side of the dark, a place where the universe breathes back out what it has taken in? If there are regions of space that act as the ultimate destination, perhaps there are also regions that act as a new beginning. If a black hole is a place where time and space seem to come to an end, the laws of physics suggest there might be a mirror image, a place where they begin. This is the theoretical concept of a white hole. In the elegant, quiet language of mathematics, a white hole is simply a black hole running backward in time. If you were to take a film of a black hole, watching matter swirl inward, light being trapped, and the silence of the abyss growing deeper, and then play that film in reverse, you would be looking at a white hole. It is a strange and beautiful thought to hold as you drift toward sleep. While a black hole has an event horizon that nothing can escape, a white hole has an event horizon that nothing can enter. It is a no-entry zone of the cosmos. No matter how much energy you used, no matter how fast you traveled, you could never step inside. It is a region of space that is permanently, perfectly full, constantly pouring matter, energy, and light out into the void. Imagine a fountain in a quiet, moonlit park. The water bubbling up from an unseen source, flowing outward to fill the basin and then spilling over the edges. A white hole is a cosmic fountain, a spring of pure radiation and particles that appears in the vacuum, illuminating the darkness with a sudden, generous glow. You might wonder why, if the math allows for such things, we have never actually seen one. We have captured the silhouette of a black hole in the heart of distant galaxies, but the sky has remained seemingly empty of these luminous twins. This is where the tension lies between what is possible on a chalkboard and what survives in the vast reality of space. Many physicists believe that white holes are inherently unstable. They might exist for only the tiniest fraction of a second, vanishing as quickly as a soap bubble, or they might be so rare that they hide in the stretches of the universe where our telescopes have not yet lingered. Some scientists even suggest a more profound possibility, that the Big Bang itself was the ultimate white hole, a single, massive outpouring of space and time that began from a point where nothing could have existed before. In this sense, every star we see and every breath we take is part of the aftermath of a white hole's first great exhale. It is a comforting image, replacing the fear of a cold, empty dark with the promise of an overflowing, eternal source of light. There is a certain poetry in this symmetry. The universe seems to love balance, positive and negative, light and shadow, beginning and end. If black holes are the quiet collectors of the universe's history, white holes are the storytellers, releasing energy back into the grand design. But this leads us to a fascinating question about the plumbing of the universe. If there is a drain and there is a fountain, could there be a hidden tunnel connecting the two? Could the matter that falls into the dark heart of a black hole find its way through the very fabric of reality to emerge renewed and radiant from a white hole in a completely different part of space, or even a different time? This connection, a bridge through the unknown, is perhaps the most famous secret passage in all of science. This secret passage is known to scientists as a wormhole. It is a shortcut through the very fabric of space and time, a bridge that defies our usual understanding of distance. Imagine for a moment that the universe is like a vast, soft sheet of fabric. If you wanted to travel from one side of the sheet to the other, you would normally have to walk across the entire surface, a journey that could take lifetimes. But what if you could fold that fabric? What if you could bring those two distant points together until they merged, and then simply step through from one to the other? This is the essence of a wormhole, a fold in reality that brings the far reaches of the cosmos right to our doorstep. In the mid-1930s, Albert Einstein and his colleague Nathan Rosen looked deeply into the math of general relativity and found that these bridges were theoretically possible. They called them Einstein-Rosen bridges. In their calculations, the throat of a black hole could, in theory, lead to another point in space-time. It was a revolutionary idea, suggesting that the universe might be riddled with hidden back alleys and secret tunnels that bypass the long, lonely stretches of the vacuum. However, as beautiful as the math is, there is a gentle tension in the physics. These bridges are incredibly fragile, far more delicate than the stars themselves. According to our current understanding, the moment a wormhole forms, the immense force of gravity would want to pinch it shut. It would collapse in an instant, faster than a pulse of light could pass through it. To keep such a doorway open, we would need something very special, a substance that scientists call exotic matter. This exotic matter isn't like the atoms in your body or the stone of a planet. It would possess a strange kind of negative energy that acts as a cosmic doorstop. While normal gravity pulls things together, this negative energy would push outward, holding the throat of the wormhole open against the crushing weight of space-time. It is a bold theory because, while the math allows for it, we have yet to find a single speck of this exotic matter in the observable world. It remains one of those forbidden ideas, a possibility that sits just on the edge of what we can prove, waiting for a future discovery to bring it into the light. But let yourself dwell on the payoff of such a thought. If wormholes do exist, the universe becomes a much smaller, more intimate place. The dream of instant travel across the stars transforms the cold, infinite void into a series of connected rooms. It suggests that we are never truly isolated. The most distant galaxy, billions of light years away, might be just a short walk through a shimmering corridor. It is a comforting vision of a universe that is not a collection of lonely islands, but a grand interconnected web where every corner is reachable and every mystery is within our grasp. Even as we look for these hidden doorways, we can see that the universe is already in motion, guided by forces we are only beginning to name. We don't need a wormhole to know that we are being moved by something vast and unseen. Right now, as you rest, our entire galaxy is being pulled through the darkness. There is a silent, powerful tugging at the heart of our cosmic neighborhood, a mystery that is drawing us toward a specific hidden point in the deep sky. This point is known as the Great Attractor, a name that suggests a vast, invisible hand guiding the motion of everything we know. For decades, astronomers noticed that our galaxy, along with hundreds of thousands of others in our neighborhood, wasn't just drifting aimlessly. We are all sliding toward a single destination at a speed of over 2 million kilometers per hour. It is a motion so grand that it encompasses entire clusters of galaxies, yet for a long time, we couldn't even see what was pulling us. The Great Attractor remains hidden behind what scientists call the zone of avoidance. This isn't a place of danger, but rather a curtain of mystery. It is the region of the sky obscured by the thick clouds of gas, dust, and stars that make up the disk of our own Milky Way. It's as if we are trying to look out of a window that is covered in a heavy velvet drape. We can feel the pull from the other side, but we cannot easily see the source. This hidden nature adds a layer of quiet tension to the discovery. What could possibly be so massive, so heavy, that it can command the movement of millions of light years of space? For a long time, it was a forbidden mystery, a puzzle that seemed to defy the simple maps we had drawn of the heavens. Some wondered if it was a colossal concentration of dark matter, or perhaps a supercluster of galaxies so dense it warped the very fabric of the local universe. But as our telescopes grew more patient and our sensors more sensitive, we began to see through the dust using infrared and X-ray light. We discovered that we are part of something much larger than we ever imagined, a vast supercluster called Laniakea, a name that means immeasurable heaven. Think of Laniakea as a great cosmic watershed. Just as rain falls on a mountain and flows down into specific valleys and rivers, the galaxies in our part of the universe flow along gravitational pathways. We are not lost in the dark. We are part of a grand flowing cosmic river. The Great Attractor is simply the low point of that valley, the place where all the paths converge. There is a deep comfort in this realization. Even in the vastness of space, there is a sense of direction. We are traveling together, cradled by gravity, moving in a slow, rhythmic dance toward a common center. This flow reminds us that the universe is structured, even when it looks like a void. But as we map these rivers of light and gravity, we sometimes find places where the flow seems to break, or where the map simply goes blank. If the Great Attractor represents a place of immense presence and pull, there are other regions that represent a haunting, beautiful absence. On the other side of the cosmic map, far from the bustling rivers of Laniakea, lies a region that is strangely empty and quiet. It is a bruise on the skin of the early universe, known as the Eridanus supervoid, a place where the light of the beginning of time seems to have faded into a mysterious chill. If the Great Attractor is a place where everything gathers, the Eridanus supervoid is its quiet, lonely opposite. To understand it, we must look back to the very beginning of time, to the oldest light we can possibly see. Scientists call this the cosmic microwave background, a faint golden glow that fills every corner of the sky. It is the afterglow of the Big Bang, a snapshot of the universe when it was just a few 100,000 years old. Usually, this light is remarkably smooth, like the surface of a still pond. But when we look toward the constellation of Eridanus, we find something that doesn't quite fit the pattern. We find the cold spot. The cold spot is exactly what it sounds like, a region of the sky that is significantly colder than everything around it. In the context of the early universe, colder means there is less energy, less data, and a strange, lingering silence. For a long time, this was a mystery that kept cosmologists awake at night. It is vast, nearly 1 billion light years across, and it appears like a shadow on the map of the heavens. Some believe it is simply a supervoid, a place where gravity has pulled matter away over billions of years, leaving a hollow space in the fabric of the cosmos. But the math doesn't always add up. The spot is too cold, too large, and too distinct to be easily explained by our current models of how the universe grew. This is where the theory becomes truly bold. Some physicists suggest that the cold spot isn't just a random void. They propose that it might be a collision scar, a mark left behind from a moment eons ago when our universe bumped into another universe. Imagine two soap bubbles drifting through the air, gently touching for a brief second before pulling apart. That point of contact would leave a trace, a disruption in the perfect curve of the bubble. If this theory is true, the Eridanus supervoid is a physical piece of evidence that our universe is not the only one. It is a window into the multiverse, a sign that we are living in just one bubble among an infinite sea of others. There is something deeply peaceful about this idea. It takes the cold, empty silence of the void and transforms it into a connection. It suggests that we are part of a much larger neighborhood than we ever dared to dream. We are not drifting in total isolation. We are surrounded by other worlds, other realities, all vibrating and drifting in a vast, unseen ocean. The cold spot is like a fingerprint, a gentle reminder that there is something beyond the horizon of what we can see. As we sit with the scale of these massive cosmic structures, the rivers of galaxies, and the bruises between universes, our minds naturally begin to drift toward the smaller details of existence. If the universe is so vast and interconnected, so full of movement and interaction, we must ask ourselves about the life that dwells within it. Does life always begin in the quiet cradle of a single planet, or is it, too, part of this grand cosmic flow? Just as galaxies drift along gravitational rivers, perhaps the very seeds of life are also travelers, drifting through the darkness to find a home. This brings us to a theory that is as old as our curiosity about the stars: the idea of panspermia. It is a word that sounds technical, but its meaning is quite poetic. It suggests that the seeds of life are not confined to a single world, but are scattered across the cosmos, drifting through the dark on the backs of comets and the hearts of meteorites. For a long time, we believed that life on Earth was a unique, localized event, a one in a billion miracle that happened in our own warm, shallow oceans. But panspermia asks us to consider a different story. It asks us to imagine that life is a traveler, a stowaway that hitches a ride on the very debris that formed our solar system. Think of a tiny microbe, smaller than the eye can see. In the harsh, freezing vacuum of space, most things would perish. But we have discovered organisms on Earth, called extremophiles, that can survive the impossible. They can endure extreme radiation, the absence of air, and temperatures that would freeze a shadow. They go into a deep, dreamless sleep, waiting for the right conditions to wake up. Scientists have found that some bacteria can survive for millions of years in this state of suspended animation. When a comet or an asteroid strikes a planet teeming with life, it can kick rocks and dust into space, carrying these tiny passengers with it. These rocks then drift for eons, eventually falling like shooting stars onto new worlds. They are cosmic messengers, bringing the blueprints of biology to any planet ready to receive them. There is a certain strangeness to this idea, a subtle tension that can feel a bit unsettling at first. If panspermia is true, it means that we might be aliens to our own planet. It suggests that our deepest ancestors may have begun their journey billions of miles away, perhaps on a young Mars or even in a distant star system that no longer exists. It challenges our sense of belonging to the Earth, making us wonder if we are merely visitors in a world we thought was our only home. But if we look closer, this bold theory is actually deeply comforting. It means that life is not a fragile accident that happened just once. Instead, it suggests that life is a fundamental property of the universe itself. It is a persistent, quiet force that refuses to be extinguished, spreading itself through the galaxy like dandelion seeds caught in a gentle breeze. We are not an isolated fluke. We are part of a grand biological tapestry that spans the light years. If life is scattered like seeds, then the universe is not a cold, empty void, but a vast, silent garden waiting for the right moment to bloom. Yet, if the universe is a garden, and the seeds of life are being scattered so freely into every corner of the dark, it raises a profound and quiet question. If life is everywhere, if it is hardy enough to survive the voyage between the stars and patient enough to wait millions of years for a home, why is the sky so silent? If the galaxy is full of these cosmic seeds, we might expect to see a universe brimming with civilizations, all grown from the same ancient source. And yet, when we look up at the night sky, we hear nothing but the soft hum of the stars. This silence has a name, the Fermi paradox, and it leads us to another theory, one that suggests we might be being watched, but from a very respectful distance. The silence of the stars is a mystery that has puzzled the greatest minds for decades. If life is as common as the theory of panspermia suggests, and if the universe is as old and vast as we know it to be, then why is the sky so quiet? One of the most intriguing and perhaps slightly bold answers to this question is known as the zoo hypothesis. This theory suggests that we aren't alone at all, but rather we are living in a sort of cosmic nature reserve. Imagine for a moment a vast galactic community that has existed for millions of years longer than our own. These civilizations may have reached a level of maturity where they understand the delicate balance of life, just as we might observe a family of rare animals from a hidden blind, ensuring we don't disturb their natural behavior or change the course of their development. These advanced beings might be observing us from the shadows of the deep. They might have a pact, a universal agreement to let emerging species like ours grow and learn on our own without the overwhelming influence of a much older, much more powerful neighbor. In this view, the silence we hear isn't a sign of an empty universe, but a sign of a respectful one. It is the great silence of a library or a protected park. However, this idea is often met with hesitation by mainstream SETI scientists, those who search for extraterrestrial intelligence. They find it difficult to lean into the zoo hypothesis because it is nearly impossible to test. Science thrives on evidence, on things we can measure with telescopes and radio dishes. The zoo hypothesis, by its very nature, suggests that the evidence is intentionally being kept from us. Because we cannot prove that something is choosing to be invisible, many researchers categorize this theory more as philosophy than hard physics. It challenges the standard scientific method, which prefers explanations that don't rely on the hidden intentions of others. But if we set aside the need for immediate proof and simply sit with the idea, there is a profound and gentle comfort to be found here. Instead of the universe being a cold, indifferent void where we are a lonely accident, the zoo hypothesis suggests we are being protected. It implies that we are being allowed to find our own way, to make our own mistakes, and to grow at our own natural pace, like a seedling in a sheltered garden. It suggests that the adults of the galaxy are watching over us, waiting for the day when we are ready to join the conversation. It turns the terrifying vastness of space into a nursery, a safe place where the silence is not a void, but a soft, watchful peace. Even as we look out toward these distant, silent stars, we are reminded that mystery doesn't only exist in the far reaches of the galaxy. Sometimes the things that are hidden from us are much, much closer to home. We often think of our own solar system as a completed map, a familiar neighborhood where every house has been accounted for. We have our sun, our 8 planets, and the cold, icy rocks of the Kuiper Belt. But as we peer into the dim, frozen outskirts of our own backyard, astronomers have begun to notice something strange. There are ripples in the dark, subtle tugs on the orbits of distant objects that suggest our family of planets is not yet complete. Somewhere out there, in the deepest shadows of our own system, a giant may be hiding. Imagine the solar system as a grand, silent house. We have lived here for a very long time, and we feel we know every room, every hallway, and every corner. We have the bright, warm kitchen of the inner planets where the sun's light is abundant, and the vast, cold library of the gas giants further out. But as we look toward the very back of the house, where the light of the sun barely reaches and the shadows grow long, we realize there might be a door we haven't opened yet. This is the mystery of Planet 9, a ghost planet that many astronomers believe is lurking at the frozen velvet edge of our sun's influence. For decades, we thought the solar system ended with Neptune, or perhaps the scattered icy debris of the Kuiper Belt. But as our technology improved, scientists began to map the paths of the most distant icy rocks in our neighborhood, objects so far away they take thousands of years to complete a single journey around the sun. As they plotted these paths, they noticed something peculiar. These rocks weren't drifting randomly, as you might expect in the lonely reaches of space. Instead, their orbits were clustered together, tilted and stretched in a way that seemed mathematically impossible if they were alone in the dark. It was as if an invisible shepherd was guiding them, a massive weight pulling on their paths with the steady, silent hand of gravity. To explain this strange alignment, researchers proposed the existence of a 9th planet, a world perhaps 5 to 10 times the mass of Earth, hidden in a deep elliptical orbit far beyond anything we've ever visited. This isn't just a small rock, it's a giant, a super-Earth, or a mini-Neptune, reigning over a kingdom of ice and shadows. It would be a world of eternal twilight, where the sun appears as nothing more than a particularly bright star in a forever black sky. The mystery, of course, lies in the fact that we haven't seen it yet. We have some of the most powerful telescopes ever built, and we have a general idea of where it should be. So, why does it remain a ghost? The answer lies in the sheer humbling scale of the search. Planet 9 is estimated to be 20 times farther from the sun than Neptune. At that incredible distance, it reflects almost no sunlight, making it thousands of times fainter than the planets we can see with a simple telescope. It moves through its orbit with agonizing slowness, taking perhaps 20,000 years to make one trip around the sun. Searching for it is like looking for a single, dark marble hidden somewhere in a vast, darkened stadium, using only a tiny penlight. There is a profound and gentle excitement in this mystery, It reminds us that even our home, this small corner of the cosmos we call our own, still holds massive secrets. We are not living in a finished, fully mapped museum. We are living on a frontier. The idea that a giant world could be hiding right in our own backyard, just waiting for the right moment to be revealed, makes the universe feel alive and full of wonder. It teaches us that there's always more to learn, even in the places we think we know best. But as we continue to scan the darkness for the faint glint of a planet's surface, some scientists have begun to whisper a bolder, more startling theory. They wonder if the reason we can't find Planet 9 with our telescopes is that it isn't a planet at all. What if the gravity we're feeling, the force that is tugging on those distant icy rocks, comes from something much smaller, much darker, and far, far older than any planet in our system? What if we are looking for a world when we should be looking for a remnant from the very beginning of time? This brings us to one of the most fascinating and, in its own way, quietest theories in modern astronomy. What if the ghost we are hunting is a primordial black hole? To understand this, we have to look back far beyond the birth of the sun or the planets, to the very first moments of the universe's life. In those initial flickering seconds after the Big Bang, the universe was a chaotic, incredibly dense sea of energy. It wasn't smooth. It was textured, with some areas being slightly more crowded than others. In these tiny, high-pressure pockets, the density was so great that space-time simply folded in on itself, creating black holes that had nothing to do with the death of stars. Unlike the giant black holes that sit like anchors at the centers of galaxies, these primordial versions could be quite small. If the object at the edge of our solar system is one of these ancient relics, it wouldn't be a vast, gaping maw. Instead, it would be roughly the size of a grapefruit, or perhaps a bowling ball. It is a thought that boggles the mind, something so small you could imagine holding it in your hands, yet so heavy that it carries the mass of 5 or 10 Earths. It would be perfectly black, perfectly silent, and almost entirely invisible, revealing itself only through the gentle, persistent tug of its gravity on the icy rocks nearby. The difficulty in finding such an object is immense because it is so small and emits no light of its own. Our traditional telescopes would never see it. We would have to look for the way it subtly bends the light of distant stars passing behind it, a phenomenon known as microlensing. It is a search for a shadow within a shadow. Yet, some scientists wonder if the universe is actually teeming with these tiny, invisible seeds. If they exist in great enough numbers, they could solve one of the greatest mysteries in science, the nature of dark matter. We know there is an extra gravity holding galaxies together, but we can't see what's causing it. Perhaps it isn't a strange new particle, but trillions of these grapefruit-sized black holes scattered across the cosmos like dark pearls in a vast ocean. There is something deeply peaceful about the idea of these primordial objects. They would be the ultimate survivors, tiny, sturdy remnants of the moment the universe was born. They are like cosmic time capsules, unchanged for nearly 14 billion years. While stars have ignited and faded, and while planets have formed and crumbled into dust, these little points of ancient gravity have remained exactly as they were at the dawn of time. They are silent witnesses to every chapter of the cosmic story. But as we contemplate these tiny anchors of mass, we begin to realize that gravity does more than just pull on objects in space. It has a much stranger, much softer effect on the very fabric of reality. It changes the way time itself flows. To get closer to a heavy object, whether it's a planet, a star, or a tiny primordial black hole, is to step into a place where the seconds stretch and the rhythm of existence slows down. It reminds us that time is not a rigid clock ticking away for everyone at the same speed, but a fluid, gentle river that bends and ripples depending on where you stand and how much weight you carry with you. Imagine, as you lie here, that the very air around you is part of a gentle, invisible tide. We often think of time as a cold, mechanical thing, a series of rigid clicks on a clock that never change their rhythm. But the deeper we look into the heart of the universe, the more we realize that time is actually soft. It is a fluid, stretching fabric that responds to the world around it. This is what scientists call time dilation. It sounds like something from a dream, but it is a fundamental truth of our reality. It means that gravity, the same force that keeps your feet on the ground and the planets in their orbits, actually pulls on time itself, slowing it down. The stronger the gravity, the more time begins to linger like a heavy syrup pouring slowly from a jar. To see this in action, we don't even need to look at distant black holes. We can see it right here on our own beautiful Earth. If you were to take two perfectly synchronized, incredibly precise clocks and place one at the very top of a high, quiet mountain and the other deep down at sea level, something strange would happen. Over many years, the clock on the mountain would tick just a tiny bit faster than the one by the ocean. Because the clock at sea level is closer to the center of the Earth's mass, it feels the planet's gravity more strongly, and so the time it measures is pulled, stretched, and slowed. If you lived your entire life on that mountain peak, you would technically be a few nanoseconds older than someone living on the beach. It is a difference so small, we can never feel it with our own senses, yet it reveals a profound secret. Time is not a single, rigid line that everyone walks at the same pace. It is a soft, shifting landscape. Even the GPS satellites that help us find our way across the world have to account for this. Because they are further away from Earth's gravity, their clocks tick slightly faster than the ones on our phones. If engineers didn't adjust for this tiny drift in time, our maps would be miles off within a single day. This brings us to a realization that can feel a bit startling at first, but is ultimately quite peaceful. It means that there is no such thing as a universal now. The now you are experiencing as you listen to my voice is slightly different from the now of a star billions of miles away, or even the now of an astronaut orbiting high above the atmosphere. There is no master clock in the center of the universe keeping track of a single objective moment. Instead, every point in space has its own rhythm, its own unique heartbeat of time. When we let go of the idea that there is one correct time, we can begin to feel untethered from the strict schedules and the ticking pressure of the world. We realize that time is more like a gentle, winding river than a cold, ticking metronome. It bends around corners, it slows down in deep pools of gravity, and it rushes a bit faster in the open spaces between the stars. It is fluid, it is soft, it is forgiving. In this vast cosmic ocean, you are not bound by a single unforgiving beat. You are part of a reality that allows for stretching and lingering. You can imagine yourself floating in a place where time slows to a crawl, where a single breath could last an eternity, and where the rush of the day simply dissolves into the quiet, heavy pull of the universe. But as we contemplate this fluid, bending nature of time, we cannot help but notice one strange thing. No matter how much it stretches or slows, time always seems to move in one very specific direction. It flows from the past through the present and into the future like a one-way street in the dark. We remember what happened yesterday, but we cannot see what will happen tomorrow. We see a glass fall and break, but we never see the shards lift themselves off the floor to become whole again. Why is it that the universe, in all its complexity, has chosen this single forward arrow? This one-way movement is often called the arrow of time. It is a concept that feels so natural to us that we rarely stop to ask why it exists. We remember our childhoods. We remember the soft light of this morning sunrise. And we remember the words of a conversation we had yesterday. But the future remains a blank canvas, a mist we have yet to walk through. This asymmetry, this profound difference between what was and what will be, is tied to a fundamental law of the universe called entropy. Think of entropy as a measure of how messy or disorganized things are. Imagine a deck of cards. If you arrange them perfectly by suit and number, they have low entropy. They are highly ordered. But if you throw them into the air and let them fall to the floor, they will almost certainly land in a chaotic jumble. That is high entropy. It is much easier for things to become messy than it is for them to become neat. In fact, the laws of physics tell us that in any closed system, disorder will always increase over time. This is why ice melts in a warm drink, why stars eventually burn out, and why we can never perfectly unstir the cream from our coffee. But this leads us to a strange tension in science. If the universe is always becoming more disordered, it means that as we look back into the past, things must have been more and more ordered. If we follow this trail all the way back to the very beginning, to the moment of the Big Bang, the universe must have started in a state of nearly perfect, unbelievable order. Scientists call this the past hypothesis. It suggests that the birth of our reality was not just a chaotic explosion, but an incredibly precise and delicate arrangement. Why the universe started in such a special, low-entropy state is one of the greatest mysteries in physics. It is as if the universe began with its bed perfectly made and its toys neatly put away, just so it could spend the rest of eternity, slowly, gently unfolding into complexity. It is a mystery that suggests there was something very specific about our origin, a starting point that set the clock in motion and gave time its direction. While the word disorder might sound a bit unsettling, this flow of entropy is actually a beautiful thing. It is the very thing that allows for life to exist. Without the movement from order to disorder, there would be no energy flowing from the sun to the earth. There would be no chemical reactions in our bodies, no thoughts in our minds, and no growth in the natural world. The arrow of time is the wind in our sails. It is what allows the universe to have a story, a beginning, a middle, and a future. It is the process of change itself, and change is what makes existence vibrant and meaningful. As you lie there, feeling the quiet rhythm of your own breath, you are a part of this grand, forward-moving story. Each moment is a new page being turned, a gentle step into the unknown. But even as we accept this one-way journey, some physicists have begun to wonder if the arrow of time is truly the only way. They ask a bold, almost impossible question. Could there be a place where the arrow points the other way? What if, at the very moment of the Big Bang, the universe didn't just move in one direction, but split into two? What if there is a mirror image of our world where time doesn't move forward, but backward? This idea is known as the mirror universe theory, and it is as elegant as it is profound. Imagine, if you will, the Big Bang not as the absolute beginning of everything, but as a point of reflection, a cosmic mirror. In this model, the Big Bang didn't just explode outward into the future we know, it also exploded backward into a twin universe that mirrors our own in almost every way, yet remains fundamentally different. While we perceive time moving toward the future, this other universe would perceive time moving in the opposite direction. This isn't just a flight of fancy or a plot for a story. It is a concept rooted in a deep principle of physics called CPT symmetry. This principle suggests that the laws of nature should remain the same if you flip three specific things: the charge of particles, their parity or left-right orientation, and the direction of time. Scientists have noticed that our universe seems to favor certain things over others. For instance, we see far more matter than antimatter, and time only ever seems to flow one way. To a physicist's eye, this looks a bit lopsided, like a scale that is tipped too far to one side. By proposing a mirror universe, the scales are perfectly balanced. In this twin world, antimatter would be the norm instead of matter, and the flow of time would be the inverse of our own. From the perspective of someone in that universe, their time would feel just as forward as ours does to us. We would be the ones who appear to be moving backward. It is a beautiful, symmetrical solution to some of the most complex questions in cosmology. It suggests that the total sum of the cosmos is zero, a perfect state of neutrality and balance where every particle has its partner and every moment has its reflection. There is a deep comfort in this idea of cosmic balance. It suggests that the universe is not a chaotic accident, but a finely tuned and symmetrical masterpiece. It means that for every action, every movement, and every tick of the clock in our world, there is a corresponding harmony somewhere else. It frames the Big Bang not as a sudden jarring start, but as a graceful unfolding in two directions at once, like a flower blooming on both sides of a mirror surface. As you settle deeper into your bed, you might find it soothing to think of the universe as this grand, balanced system. Nothing is truly lost, and nothing is out of place. We are simply traveling along one side of a great, shimmering reflection. But as we contemplate the direction and the symmetry of the universe as a whole, we are naturally led to wonder about the very substance of this reality. If time and space can be so perfectly mirrored, what are they actually made of? To find the answer, we must move our focus away from the vastness of twin universes and look instead at the smallest possible scales, the tiny fundamental building blocks that hum beneath the surface of everything we see. We are moving from the grand architecture of time to the silent, vibrating heart of matter itself. Imagine for a moment that you have a microscope of impossible power. You look at the soft fabric of your blanket. You zoom in past the threads, past the individual fibers, and deep into the atoms that make up the material. Usually, we are taught that at the very bottom of reality, there are tiny, solid points, little billiard balls of matter called particles. But there is a theory, one of the most elegant and bold ideas in all of science, that suggests something much more poetic. This is string theory. Instead of little dots of matter, string theory proposes that everything in the universe, the light from the stars, the air you breathe, and the very cells of your body, is made of unimaginably small vibrating loops of energy. Think of these loops like the strings of a celestial guitar. When a guitar string is plucked, it can vibrate in different ways to create different notes. A low resonant C, a bright G, or a soft lingering E. In the same way, these cosmic strings vibrate at different frequencies. One vibration creates an electron. A slightly different vibration creates a quark. Another creates a photon of light. It is a beautiful thought, isn't it, that the entire physical world is not made of stuff, but of music. Every object you touch is a collection of harmonies, a resonance of energy that has been singing since the beginning of time. But for this music to be played, the guitar of the universe needs more than just the 3 dimensions of space we are used to. We know up and down, left and right, and forward and back. We move through these 3 dimensions every day without a second thought. But the mathematics of string theory, the equations that describe how these strings must move and interact, simply do not work in our 3-dimensional world. They require more room to breathe. They demand a universe with 10 or even 11 dimensions. To our human minds, this can feel like a mystery too large to grasp. We look around our rooms and see only the familiar dimensions of height, width, and depth. The idea of 7 or 8 more hidden directions feels almost forbidden, a secret that the universe is keeping tucked away from our senses. Yet, if we follow the math, the reward is a vision of reality that is breathtakingly unified. It suggests that everything we see and everything we feel is part of one single grand silent symphony. In this view, there is no fundamental separation between gravity and light, or between the earth beneath you and the furthest galaxy. We are all made of the same music, played on the same fundamental strings. It is a thought that allows the mind to rest, knowing that there is a deep underlying order to the complexity of life. The universe is not a chaotic mess of random particles. It is a composed masterpiece, humming with a gentle, eternal rhythm. It is a symphony that has no conductor, yet never misses a beat. But as you lie there, drifting closer to sleep, a natural question might arise in the quiet of your mind. If these extra dimensions are real, and if they are necessary for the music of the universe to exist, where are they hiding? Why can't we see them? And how could something so vast be tucked away right in front of our eyes. To understand that, we must look at the way space itself can fold and curl, hiding entire worlds within the smallest possible spaces. To understand where these dimensions might be hiding, we can use a very simple image. Imagine a garden hose lying on a long green lawn. If you were to stand 100 feet away, that hose would look like a simple, one-dimensional line, a green stripe across the grass. From your perspective, it has only one direction, length. But imagine a tiny ant walking along that same hose. To the ant, the world is much more complex. It can walk forward and backward along the length just as you see it, but it can also crawl around the circular circumference of the hose. To the ant, there is a second dimension that you, from your distant vantage point, cannot see at all. This is how scientists believe the extra dimensions of our universe behave. They are what we call compactified, curled up so tightly and so small that they are invisible to our eyes and even to our most advanced scientific instruments. While we move through the vast dimensions of height, width, and depth, these other 7 or 8 dimensions are tucked away at every single point in space. They are not far away in another galaxy. They are right here, in the palm of your hand, in the air you breathe, and in the space between the stars. They are simply too small for us to perceive, like the circular path of the ant seen from a great distance. In some theories, our entire three-dimensional world is just a thin membrane, or a brain, floating in a much larger, higher dimensional space called the bulk. Imagine our universe as a single leaf floating in a vast, deep forest. We spend our lives crawling across the surface of the leaf, unaware of the massive trees and the wide sky that make up the bulk around us. This concept helps solve one of the greatest mysteries in physics: why gravity is so much weaker than the other forces of nature. You might not think of gravity as weak, but consider this. When you pick up a small refrigerator magnet, that tiny piece of metal is able to pull a paper clip upward, overcoming the gravitational pull of the entire Earth. The whole planet is pulling down, yet the tiny magnet wins. Scientists wonder why. A bold theory suggests that gravity isn't actually weak. It's just that it doesn't stay confined to our leaf. While light and matter are trapped on our three-dimensional membrane, gravity might be leaking out into the bulk, spreading its strength across those hidden dimensions. It is a profound realization to think that there is more to space than meets the eye, and it is all happening right in front of us. Our reality is not a flat, simple thing, but a rich, multi-layered tapestry. We are living in a house with rooms we have never entered, yet those rooms provide the very foundation that allows our world to exist. As you settle deeper into your bed, you might feel a sense of wonder at how perfectly constructed this hidden architecture is. The way these extra dimensions are curled, and the specific way they allow the strings of the universe to vibrate, is not random. It is as if the universe has been precisely calibrated. If these dimensions were shaped even slightly differently, the music of the universe would change, and the laws of physics, as we know them, might not allow for stars, planets, or even life itself. This brings us to a quiet yet striking realization. The very constants of our world seem to be tuned with an incredible, almost impossible level of precision. This brings us to a quiet yet striking realization. The very constants of our world seem to be tuned with an incredible, almost impossible level of precision. Scientists often refer to this as the fine-tuning problem, though it feels less like a problem and more like a profound mystery when you are resting in the quiet of the night. It is the observation that the fundamental laws of physics, the invisible rules that govern everything from the spinning of an electron to the birth of a galaxy, seem to be set at exactly the right values to allow for the existence of life. Imagine, if you will, a vast control panel that stretches across the horizon of the cosmos. On this panel are dozens of dials, each representing a fundamental constant of nature. One dial controls the strength of gravity. Another sets the speed of light. A third determines the mass of a proton. For the universe to produce stars, planets, and eventually people, every single one of these dials has to be set to a very specific, narrow range. Consider the dial for gravity. If gravity were just a fraction stronger than it is, the early universe would have been too efficient at pulling itself together. It would have collapsed back into a fiery crunch long before the first stars had a chance to shine. If gravity were just a tiny bit weaker, matter would have drifted apart so quickly that it never would have clumped together. There would be no suns, no earth, and no one to wonder why. The same is true for the forces that hold atoms together. If the strong nuclear force, the glue of the atom, were only 2% stronger, hydrogen would not exist. Without hydrogen, there would be no water and no stable stars like our sun. If it were slightly weaker, the only element in the universe would be hydrogen, and the complex chemistry required for life would be impossible. Our existence is balanced on a knife's edge, a perfect harmony of physical laws that allows the music of the spheres to play. This leaves us with a deep, quiet question that scientists and philosophers have pondered for decades. Why are the dials set this way? Some suggest it is simply a lucky coincidence, a 1 in a trillion roll of the cosmic dice. Others wonder if there is an underlying logic we haven't yet discovered, a single theory of everything that dictates these settings must be what they are. And then there is the possibility of the multiverse, where an infinite number of universes exist, each with its own set of dials. In that vast landscape, most universes are dark, chaotic, or empty, and we simply find ourselves in one of the rare few where the conditions are just right for us to be here, observing it. Regardless of the explanation, there is a deep sense of gratitude that comes from realizing how specific the conditions for our lives truly are. It makes the world feel a bit more precious, and your place within it a bit more meaningful. We are the witnesses to a universe that seems in its very bones to be hospitable to us. As you breathe slowly and feel the weight of your blankets, you might find comfort in the thought that the universe is not a chaotic accident, but a finely balanced masterwork. To truly understand how these dials were first set and how this balance was achieved, we have to look back even further than the stars. We must travel back to the very first second of the universe's life, to a moment of unimaginable power and growth that set the stage for everything we see today. To understand how the dials of our universe were set with such precision, we have to look back to a moment of growth so rapid and so vast that it almost defies the imagination. This is the theory of cosmic inflation, a massive growth spurt that occurred in the very first fraction of a second after the universe began. Imagine for a moment the entire observable universe as it is today. All the billions of galaxies, the trillions of stars, and the infinite reaches of dark space, all condensed down into a tiny glowing speck. This speck was far smaller than a single atom, smaller even than a proton. It was a point of pure concentrated potential, cradled in the silence of the beginning. Then, in a period of time so short it cannot be measured by any human clock, this subatomic speck underwent a transformation. It didn't just grow, it surged outward. In less than a trillionth of a second, the universe expanded by a factor of at least 10 to the power of 26. To visualize that, imagine a single grain of sand suddenly swelling to the size of the entire Milky Way galaxy in the blink of an eye. This wasn't an explosion of matter into an empty room. Instead, it was a stretching of space itself. The fabric of reality was being pulled outward in every direction at once, faster than the speed of light. As you lie here, breathing softly, try to picture that incredible, silent stretching. It was a moment of supreme order, smoothing out the universe like a hand smoothing a wrinkled sheet. This is why, when we look out at the sky today, the universe appears so remarkably uniform. No matter which direction we point our telescopes, the temperature and the density of the cosmos are almost exactly the same. Inflation took the chaotic energy of the beginning and spread it out evenly across the void. Yet, this process introduces a beautiful mystery. Scientists believe this expansion was driven by something called the inflaton field, a mysterious energy that permeated the early universe. But what turned on this field, and perhaps more importantly, what turned it off? If inflation had lasted just a tiny bit longer, the universe would have been too diluted for gravity to ever pull matter together. If it had ended too soon, the universe might have collapsed back in on itself before it truly began. The on and off switches of inflation are among the most profound secrets of physics. It was as if the universe took one deep cosmic breath, held it for the briefest of moments, and then exhaled, allowing the stars to form in the stillness that followed. There is a deep sense of awe in this creative moment of history. Within that rapid stretching, tiny quantum fluctuations, little wobbles in the energy of space, were stretched out to cosmic scales. These tiny whispers of energy eventually became the seeds of everything we see, the clusters of galaxies, the glowing nebula, and the very planet beneath you. The largest structures in existence today began as the smallest possible flickers of light during that brief, powerful growth spurt. As you settle deeper into your pillow, you might feel a sense of peace, knowing that the vastness of the cosmos was born from such a singular, focused event. It suggests that everything we see is part of one giant, connected whole. But if the universe expanded that quickly and that uniformly, it leaves us with one more question about the nature of our home. If you stretch something that much, what does it do to its form? We must now consider the actual shape of the universe. whether it is a flat expanse that goes on forever or something more curved and mysterious. If we imagine that massive growth spurt of inflation stretching the universe like a piece of dough, we have to ask what shape that dough eventually took. When you lie still and think about the space around you, it's natural to imagine it extending forever in straight lines, like the walls and floor of a room that never ends. But in the grand language of cosmology, the shape of the universe is one of the most fundamental questions we can ask. Is our universe flat, like a sheet of paper? Is it spherical, curving back on itself like a globe? Or is it hyperbolic, shaped like a vast cosmic saddle that curves away in every direction? To find the answer, scientists look at the oldest light in existence, the cosmic microwave background radiation. Imagine, if you will, 3 beams of light traveling through the deep silence of space. If these beams were to form a massive triangle spanning billions of light years, we could measure the angles of that triangle to understand the geometry of the universe. On a flat surface, the angles of a triangle always add up to exactly 180 degrees. If the universe were a sphere, those angles would add up to more, and if it were a saddle, they would add up to less. When our most advanced satellites look at the sky, they see something remarkable. To within a tiny fraction of a percent, the universe appears perfectly, elegantly flat. This flatness is a direct result of that initial inflation we spoke of. It stretched the fabric of space so much that any initial curves were smoothed out, much like how the surface of the Earth looks flat to us because we are so small compared to its great curve. But flat doesn't necessarily mean infinite. This is where the mystery deepens into something quite beautiful. Some scientists suggest a theory known as the 3 torus model. In this view, the universe is like a cosmic donut. It is mathematically flat, but it is connected in a way that loops back on itself. Imagine you are on a spacecraft traveling in a perfectly straight line through the velvet dark. In a torus-shaped universe, you would eventually find yourself returning to the very spot where you began, having traveled the full circumference of the cosmos without ever turning around. It is like those classic video games where moving off the right side of the screen brings you instantly back to the left. This creates a mental image of a universe that is finite, having a specific limited volume, yet entirely boundless, with no edges to fall off and no walls to stop your journey. It is a self-contained cozy system, a grand loop that holds everything we know within a single, continuous fold. There is a deep sense of comfort in this idea. It suggests that the universe is not a terrifying, infinite void that goes on forever into a meaningless distance, but a complete and whole structure. It is a home that is large enough to hold billions of galaxies, yet small enough to be a single unified thing. As you breathe slowly and feel the weight of your body against the mattress, you can picture the universe as this grand, silent loop, perfectly balanced and perfectly shaped. However, as we contemplate the shape of the room we inhabit, we must also consider the material it is made of. We have looked at how the universe began and how it is shaped, but we are now beginning to ask a more delicate question about the stability of the fabric itself. Just as a calm lake can appear still while hidden currents move beneath the surface, some theories suggest that the vacuum of space, the very stage upon which the stars perform, might not be as permanent as it seems. We must now turn our attention to the quiet, subtle whispers of the vacuum and the gentle, theoretical possibility of a change in the very laws of physics. To understand the stability of our universe, we must look at what scientists call the vacuum, not as a literal empty void, but as the fundamental state of space itself. Within this state exists something called the Higgs field. You can picture this field as a soft, invisible mist that fills the entire cosmos, a gentle, silent pressure that allows the stars, the planets, and even our own bodies to have mass and form. It is the quiet coordinator of reality, the background hum that keeps the physical world behaving as it should. In the world of physics, everything seeks its lowest energy state, like a marble rolling down a hill to rest at the very bottom of a valley. For a long time, we assumed our universe was already resting in that deepest valley, a state of perfect, permanent stability. However, some modern theories suggest we might be in what is called a false vacuum. Imagine that marble resting in a small dip halfway down a mountain. It feels stable. It isn't moving. It sits there, cradled by the earth, seemingly at rest. But further down, far below the ledge where the marble sits, there is a much deeper, wider valley, the true bottom of the mountain. This is the concept of vacuum decay, sometimes called the Big Slurp. The theory suggests that if a tiny patch of space were to somehow tunnel through the barrier of that ledge and drop into the lower energy state, it would create a bubble of new physics. This bubble would expand outward at the speed of light, subtly and instantly transitioning everything it touches into a different state of being. It is as if the universe decided to change the melody it was playing, shifting into a new, deeper key. It sounds like a grand sweeping change, a cosmic reorganization of the highest order. But as you lie here, safe and warm in the stillness of your room, it is important to remember the scale of time and probability we are discussing. The universe has existed in its current state for nearly 14 billion years without a single flicker of this change. It is a testament to the incredible stability of the world we inhabit. The mathematical probability of such an event occurring is so infinitesimally small that it essentially disappears into the noise of the infinite. Most calculations suggest that our vacuum is stable for trillions upon trillions of years, a span of time so vast that the stars themselves will have long since lived out their lives and faded into embers before such a thing could even be considered a possibility. In many ways, this theory is more of a mathematical curiosity than a physical reality we need to ponder. It is a reminder that the universe is a complex, multi-layered thing with depths we are only beginning to map. It is a maybe hidden in the fine print of the laws of physics, a ghost in the equations that will likely never manifest. Rather than a sudden shift in the vacuum, most astronomers believe the universe has a much slower, more rhythmic destiny ahead of it. As we move away from these sudden, theoretical bubbles of change, we find ourselves looking toward a much more certain and peaceful conclusion. It is a process not of sudden transition, but of a long, slow cooling, a gradual settling into a state of ultimate rest. This brings us to the most widely accepted vision of the far, far future, a quiet silver twilight that scientists call the heat death, but which we might better understand as the universe finally preparing for a long, deep sleep. The term heat death might sound intense, perhaps even a bit frightening, as if the universe were destined to end in a great consuming fire. But in reality, the physics describes something much more serene. It is not a burning end, but a gentle universal cooling, a slow transition into a state of ultimate quiet. Imagine a warm cup of tea sitting on a bedside table in a cool room. Over time, the heat from the tea slowly drifts into the air. Eventually, the tea and the air reach the exact same temperature. They are in equilibrium. When this happens, there is no more movement of heat, no more steam rising, just a quiet, shared stillness. The heat, death of the universe, is simply this process on a cosmic scale. It is the natural tendency of all things to move toward balance. For billions of years, the stars have been the engines of the cosmos, burning brightly and pouring their energy into the darkness. They are the sources of heat, the sparks in the night. But eventually, like a candle reaching the end of its wick, even the longest-lived stars will begin to dim. They will use up their fuel and slowly fade, one by one. The galaxies, once bustling cities of light, will grow quiet as the gas used to forge new stars is finally exhausted. The great clouds of dust will settle, and the universe will continue to stretch out, becoming thinner and cooler as the space between objects grows larger and larger. In this far-off future, trillions upon trillions of years from now, the universe reaches a state of maximum entropy. This isn't a state of chaos, but a state of perfect, unchanging stillness. There are no more hot suns or cold voids. There is only a soft, uniform temperature everywhere. It is the big sleep, the moment when the universe finally exhales and settles into an eternal, peaceful rest. The cosmic machinery, having done its magnificent work of creating life, light, and complexity, finally falls silent. It is the ultimate expression of balance, where every part of the universe is finally at peace with every other part. As you drift closer to sleep, you can imagine this state not as a cold ending, but as the universe finally finding its pillow. It is a state of perfect symmetry where nothing is out of place and nothing is rushed. It is the long, slow sigh of the cosmos. As we contemplate this vast, silent future, a curious question begins to form in the mind. If the universe is destined for such a long, quiet sleep, why do we find ourselves here now, in the middle of the waking day? Why do we exist in this brief, brilliant window of time when the stars are still bright and the galaxies are still dancing? It seems almost too perfect that we are here to see it all. This brings us to the beautiful and humbling idea known as the anthropic principle, the notion that the universe is exactly the way it is because we are here to witness it. The anthropic principle is a quiet, elegant idea that helps us make sense of our place in this vast, dark ocean of space. It suggests that the universe must have the properties it does simply because we are here to observe it. At first, this might sound like a riddle or a bit of circular logic, but it is actually a very grounded and comforting realization. Think of it this way. If you were to wake up in a house that was perfectly stocked with your favorite foods, a bed that was exactly the right softness, and a temperature that felt just right, you might be amazed by the coincidence. But the anthropic principle reminds us that if the house were freezing, or if there were no food, you simply wouldn't have woken up there at all. You're only there to ask the question because the conditions allowed you to be. We shouldn't be surprised that the laws of physics seem perfectly tuned for life. If gravity were slightly stronger, the universe would have collapsed back in on itself long ago. If it were slightly weaker, stars and planets would never have formed. If the chemistry of carbon were different, the very cells in your body couldn't hold together. We look out at the stars and marvel at how hospitable the cosmos is to us, but the truth is, we are the result of that hospitality. We are the part of the universe that has grown eyes to see itself and a mind to wonder about its origins. If the universe were any other way, there would be no one here to notice the silence. It is as if the universe is a giant puzzle, and we are the piece that finally makes the image clear. There is a deeper, more mysterious side to this idea as well, a tension that some scientists and philosophers find fascinating. It is the question of whether the universe actually needs an observer to truly exist. In the world of the very small, in the realm of quantum mechanics we touched on earlier, we know that particles can exist in many states at once until they are measured or observed. Only then do they settle into a single solid reality. Some wonder if this applies to the entire cosmos. Perhaps the universe, in its earliest days, was a vast cloud of overlapping possibilities, waiting for the first spark of consciousness to look up at the sky and define what is real. In this view, we aren't just passive travelers on a rock. We are active participants in the unfolding of reality. This brings a profound sense of connection. Often, when we look at the scale of the galaxies, we feel small and lost. We feel like tiny specks in an indifferent void. But the anthropic principle flips that perspective. It tells us that the human mind and the vast cosmos are deeply intertwined. You are the universe experiencing itself. You are the way the stars dream. Every breath you take and every thought you have is a part of the universe's own story, a moment where the silence of space finds a voice. You aren't separate from the stars. You are the stars looking back at themselves. As you lie there, feeling the weight of your blankets and the soft rhythm of your breath, you can feel that connection. You belong here. You are a necessary witness to the beauty of the stars and the mysteries of time. The universe has spent billions of years evolving, shifting, and cooling, all to reach this moment where you can close your eyes and feel at peace within it. We have traveled a long way together tonight, from the first breath of the Big Bang to the quiet stillness of the distant future. Now, as we begin to draw our journey to a close, we can look back at everything we've learned and see it not as a collection of cold facts, but as a map of our incredible home. We are ready now to take these final thoughts and let them carry us into a deep, restful sleep. Take a slow, deep breath now and let the air out gently. We have traveled a vast distance together tonight, moving through the cycles of time and the reaches of the unknown. We began with the idea of the big bounce, the universe as a rhythmic, breathing thing that has perhaps always existed and always will. We looked at the fabled Hawking points, those faint echoes of a world that came before our own. And we pondered the possibility that we are living within a grand hologram or a many worlds reality where every path is eventually taken. We explored the strange beauty of black holes and the fountain-like light of white holes. We felt the pull of the great attractor and wondered at the cold, silent spots in the sky that might be scars from a collision with another universe. From the tiny, vibrating strings of string theory to the massive, hidden presence of Planet 9, we have seen that our reality is far more complex and far more wonderful than it appears on the surface. It is natural to feel a sense of weight when we contemplate these bold theories. Sometimes the scale of the cosmos or the strange nature of time can feel overwhelming. But as we have seen tonight, what we often label as fear in the face of the unknown is actually the threshold of a new discovery. It is the feeling of the mind expanding to hold a larger truth. Every mystery we encountered, whether it was the silent vacuum of space or the invisible glue of dark matter, is simply an invitation to wonder. There is a quiet tension in the realization that we may never have all the answers. Our telescopes may never see past the edge of the observable horizon, and our math may always struggle to reach the very center of a singularity. But there is a profound comfort in that mystery. The fact that the universe remains partly hidden means that there is always room for growth, for dreaming, and for the imagination to take flight. You do not need to solve the equations of the stars to be a part of their story. You do not need to map every hidden dimension to feel the harmony of the world around you. As you lie here in the stillness, let the day's worries drift away like stardust. The questions of how and why can wait for tomorrow. For now, the only reality that matters is the rhythm of your breathing and the warmth that surrounds you. You are a part of a grand, ancient, and beautiful system. You are safe within the vastness of the cosmos, a witness to its wonders, and a participant in its peace. The universe is cooling, the stars are shining, and the great clock of time is ticking at a slow, gentle pace. Everything is exactly as it should be. You have done enough for today. It is time to let go of the thoughts of the journey and embrace the stillness of the destination. Let your mind become as quiet as the space between the galaxies. Let your heart beat in time with the slow, steady pulse of the universe. Thank you for joining me on this journey through the stars. May your dreams be filled with the light of distant suns and the peace of the infinite void. Close your eyes now. Let the world fade to black and drift into the deep, restorative rest you deserve. Sleep well, sleep deeply. Good night.